Hello everyone. So welcome to this video. Today we are going to go over the cross-validations approach for model selections. I have some people telling me that they would like to review this topics because we only have the class one time to go over the validations approach. So today we are going to try to use some examples on in R, and also hopefully while we are doing this coding in R, I can also utilize the whiteboard functions on Zoom to very simply break down the logic of this validation approach. So it's going to be a short video, so don't expect me to go into too much of a details to explain the code, but whether to understand how the code relate to the theory in the background. All right, so let me share my our screen right here. All right, so as you can see, I'll have a file here called DS612 our codes cross-validation review. You can now download them in my GitHub post. I update these files on my GitHub, so you can actually download this files to your working folder, or you can actually download the whole thing, right? All right, so today we are going to do a very simple job right here. We are basically trying to demonstrate the use of cross-validations for model selections. So we're going to use a very simple example here. So please get up with us. So first of all, we are going to call out the ISLL package because we're going to use the auto data sets from the ISLL package. And we're going to also use the, I think the boot package. I'm not quite remember, but probably we do. All right, so let's do this. So first, attach the data sets. Right. So if you want to know what the auto data set is, again, is the cells of auto, not the cells, but the auto performance. Right. So MPG, cylinders, displacement, horsepower, everything about cars. If you want to do the pair parts, you can do the pairs functions again to see what are the highly correlated variables in this data set. So today our objective is to find the good model, right? So or a better model in order to make predictions. So we are going to utilize the cross-validations technique. So first of all, I'm going to split the data into two sets. One is the testing set and the other one is the training set. So here I'm going to set the random seed here. I'm going to set the sampling methods here, right? So we sample the total of 392 observations. We only picked 300 out to set as a train data. So we set the train. So this is the train index. We are going to have the test index, which is anything that's not included in the training. And we are going to create a training data sets here and a testing data sets here. So again, if you are not following very well in this video, don't worry, there's always a code available for you to try. So please spend some time to play around with this data set and the code that I provided for the class. So here we are going to basically create a outcomes. So we have the training outcomes here, which is the MPG, which is the outcome, the response variable from the training sets. And we're going to create a testing outcomes, which is the MPG from the testing sets. All right, so what we're going to do first is that we are asking the following questions. So I have this three models here. So fit one, it's basically using only horsepower to predict MPG. And we're using the training data sets. And the second one is using the horsepower and the weight of the car to make a predictions on MPG. And we're using, again, the subsets of the data. So I'm using different methods here or putting different arguments here to demonstrate there are multiple ways for you to actually call the data. Remember, we created the training data sets already here. So we can actually use it. Or if you want to actually call a subset of data, so you can actually call the subset by basically just putting the index of the subset. So the train basically store all the index, right, that we use for the subset data. Or if you want, you can actually put in data and then just using the index methods to call the training data sets, right? So either one way or the other. So basically I have three models here: the horsepower that explain MPG, the weight and horsepower explain MPG, and the last one here is horsepower, weight, and displacements to explain MPG. So we want to actually ask the following questions. So which one is the better model to use for making a predictions for MPG? Of course, in the reality, we know the MPG cannot be easily predicted, right? In this data set, we should actually have more other variables to include it. But let's say you only have three, and you want to find out which one should be included, or which one it's included, how complicated the model should be in order to answer the question. So which model would be better? So now we have three models we want to compare. If we are only using the criteria to evaluate the model like in the past, let's say looking at the adjusted R square, or maybe the F statistics, or maybe the efficiency of the significancy of the coefficients, those are basically criteria that help us to understand the models, how well it fits the training data sets. Again, we do not know how well it used to predict the testing data sets. So we would like to actually apply the validation set approach here first in order to see which model would be a better model for predictions for the unknown data. All right, so the validation set approach, it's pretty simple. And here, I'm hoping that no one is confused. So I would like to basically switch back on the whiteboards so that I can explain a little bit about the idea. So the idea for using a validation set approach, again, a validation set approach. It's basically trying to split the data that we have, right? So this is the data we have into two subsets. One is called training, and the other one, it's basically for testing. We will train the models using the data sets that we have in the training data subsets. So this will be used to train the models. Once we have the models from this training data sets, once we fit the model, right, with the data sets, what we want to do is to basically put in the testing data sets in this model and trying to see how well the model can predict the unknown data sets, right? So the predictive powers. So it's as simple as that. So we want to use the validation set approach. Well, since we already separate the data into a training set and a testing set, so we can easily take this approach and trying to evaluate the predictive power of each model when they face a unknown data. So let's come back here. So let's go back here and let's see. Let's go back here to the outputs here. So what we're going to do is to basically calculate the marginal, not marginal, but the the mean square error of the testing data. So, well, we can actually do the training MSE first, right? By basically subtracting the data sets values, right? The actual values of MPG, and by the predictions. And then we have to call the training here, right? So this is for training data only. So we do this, and we calculate the training's mean square error, which is 23.911. And here we're going to basically calculate the testing, right? So this time we are not including the training data sets, right, from auto, but we are only including testing, right? So we take out the training, the only leftover will be the testing. So we're gonna calculate this, and we got 24.4044, So that's basically the mean square error for training and testing from the first model, right? Fit once. And we want to compare, right? So we want to know how well it does for the second models. So we're gonna basically, again, you can have multiple ways to do this. I'm going to use this predict fit2. And this time I directly pass in this training data sets, right? So instead of calling out train here, I can actually use the training data sets, right, as my data for predictions. And after that, well, I'm going to use the predictions minus the actual training outcomes, right? The actual values from the training data sets for MPG. So we run this, and we get the mean square error for the training data sets from model 2. And of course, if you want to pass in the testing data sets here, to repeat the same thing, right? So you do this, you make a predictions, and then you compare the predictions to the actual testing data set results, the MPG in testing sets. And we got a testing error, 16.53. And now we're gonna test also the third model. The third model is the most complicated one, right? So we have 3 variables instead of 2 comparing to the second models. So we do the same thing. The training mean square error, 18.21. For the testing data sets, we're going to calculate the mean square error, and we get 16.78. Now, at this point, you might actually confuse, hey, how come I'm getting all this number? I don't know how to interpret them. So don't worry, let's plot them out, right, to see what it means. So let's save this as model fit1, fit2, fit3. And we're going to create some x-axis for plotting later. And we're going to basically create the vector for the training MSE and the testing MSE. And we're going to put them into a data frame. So we can actually see it from a data frame format here, right? So this is basically how each model behave. So fit1 has a very high error terms, right? So the mean square error. Well, compared to model 2, we have a lower mean square error, right? Reduced significantly by adding 1 more variable in there. But the third ones, well, there's a problem. The third one doesn't seem like, well, a lot of improvements, or in some cases, right, the testing error, it's actually much higher. Not much, but at least higher than the second model, which suggesting the third model here, fit3, even though it's more complex, but then it's not good for making a prediction for the unknown data sets. Again, you can plot this results. So I'm going to use the blue lines to start with the plots to basically plot the testing MSE in the graph. So this is basically results here. And we're going to add a line to this graph. So we will have a red lines that represents the training mean square error on the same plots. And then you can actually give it a legends here. So if you want, you can actually say, okay, so this is basically the 2 lines, right, representing each of the model. So obviously, both the testing MSE and training MSE seems to be in line. And of course, in this case, we trust the testing MSE much more, not because it has a lower value, but it's only because the testing MSE actually tell us how well the model will predict the unknown, unseen data sets. And seems like the second model is superior comparing to the first and the third model. So that's basically what we call a validation set approach. Now, what we want to do, it's basically use the cross-validations approach. So again, cross-validation involved with different degree of k value you can choose. To the extreme, we can actually use the leave one out approach. What it means is basically we are actually shuffling the data. And again, I'm going to use the whiteboards a little bit here. So the live one out approach. So the live one out, LOOCV, cross validations, basically suggests that we have this one big box of data. And we are going to shuffle the data one time. And the first time we do, so the first time, we will have one data observations. So let me just make it a little bit larger. So we will have the first observations. To draw out, so let me just use a shorter term here. So make it a little bit easier to read. So the first observations, and the rest of the data will goes into this box right here, right, the rest. So what we're trying to do in this first resampling is that we are going to use this majority of the data to train the model. And it will come up with a model fit. All right, so we have a model here. And we're going to pass in this first observations into the model and trying to make a predictions. So we finish this process one time. And what happened is we are going to redo this process again. And in the second time, well, we are going to draw the second observations from the data sets. And for the rest of the data still goes into this box, and they will be used to train, of course, including the first observation this time. And then it will goes into the model, and we are going to basically pass in the second observation into this new model and trying to make a new predictions to see how close our prediction to the actual values from the second observations. And this process will repeat itself, right? So it will keep repeating. So it will go to the third time, and then so on and on. So how long this process will last? This process, so this process will repeat n time. And n here represent the total number of observations from your data sets. So until we draw every single one observation out for this process to test its predictions, well, we are going to continue to do it. So this is basically the reason why we call this a leave one out cross validations, because every time we leave one observation out and we use the rest to train. So this is basically the idea for a leave one out approach. So again, well, let's go back to our out settings. So in this approach, again, well, it's very similar. Again, I'm not going to go over the details, right, from the modeling. So I'm going to fit the data, everything we have. Okay, so in this cross-validation approach, you do not need to use the training set or the testing set. You just pass in the whole thing. You train the data with the model specifications. Well, this time we have MPG to horsepower. And then you can see the fits here. And you are going to fit the second model, right? Horsepower, weight that used to predict the MPG. And then the third models, exactly the same thing, horsepower, weight, and displacement. All right, so once you get to this point, the leave one out cross validations marginal, the mean square error, it's very, very easy to get. You do not need to pass in the testing sets and then the training sets, right? So you don't have to create that one observation yourself. There is a very simple way how you can do the leave one out cross validations mean square error. So you can actually use the cv.glm functions. You pass in the data, and then you pass in the fits of the models, and you will be able to get the results from the delta outputs. So let's run this. And here you have the mean square error equals to 24.23. So again, this is the average mean square error after the model run n time. So how many observations we have? We have 392 observations in this data set. And that means, well, this cv.glm, it's actually using the fit1 specifications to run the model 392 times. And then it stores the values from each models and calculate the aggregates, the average mean square error from each model, and report it in the delta. So that's basically the mean square error from the cross-validations leave one out approach. We also talk about we can use the cheating forms for linear regression models. So as long as you have a linear regression model, you can actually apply these functions here. Right? So you can actually calculate the importance of the models. This is the importance of the model specifications. And then you can basically use the residual of the fits divided by 1 minus h to the square, and then take the mean values of the sum. So we went over this in the lecture, and also it's in textbook. So please review these equations if you don't feel comfortable with this. So we do this, and then we can actually use the functions now, LOOCV, that we just defined here, to calculate the cross-validation, leave one out cross-validations mean square error for fit2. And then you can see this here. So this is the result. So 18.1129. And the third model here, again, we are going to use the cheating formula here because it's so fast. It doesn't fit the model like 392 times in this case. It only fit the model one time, and then we are just extracting the importance the h variable here, the importance parameter from the models, from the full models, so that we can actually use it to calculate the leave one out values. So here we use the LOOCV, and then we have a value here, 18.18. So again, so at this point, you can actually store these values into a vector and then trying to put it into a data frame like we did before, and see how each model can make a predictions for the unknown data. Right? So in this case, it seems like fit2, it's still a better one. So it's consistent with our previous validation sets approach. Again, if you want to actually add this to your previous graph, you can actually add a line. So I'm going to add a green lines to the existing graph. And this time we're reporting the leave one out cross-validations results. Okay, so we have that. So I'm gonna make this a little bit larger for you to read. And I'm gonna add the legends here so that you know there are 3 lines here, 3 colors of lines. All right, so seems like we are getting consistent results. So that's good news, because if one contradict with the other ones so much, then we will be confused about like which approach we should use. But seems like, well, the validation set approach and the leave one else approach are consistent. Now you are going to try to use maybe the k-fold. So let me use the general name here, k-fold cross-validations approach. So this time we are going to use a 5-fold cross-validations and a 10-fold cross-validations to check the model fits. I mean the predictions. Okay, so the only thing you need to do here, it's basically pass in the full model fit once into this cv.glm. Well, for a 5-fold cross-validation, you have defined this k arguments in the functions. So you have to put k equals to 5 to indicate you are using a 5-fold cross-validations. So again, well, in a 5-fold cross-validations, what happened is we are basically just using 5 subsets of data to define the data, the observations, right, as a training set and a testing set. So again, well, let me use the whiteboard a little bit here just to go over the concept with you guys one more time. So in the k-fold cross-validations, so what happened is we are going to define k. So let's say k is equal to 5. So what it means is we begin with, again, our original data sets, right? A big box of data. That's really ugly here. So data. So this data set is going to be split into 5 boxes, right? So as we define here, we're going to split this into 5 boxes. So we have box 1, we have box 2, we have box 3 and 4 and 5. So that's basically what the 5-fold means. So we're going to create these 5 boxes. And we are going to use these 5 boxes. Again, well, samples are, observations are randomly assigned to these boxes. So randomly assigned. So observation randomly assigned to these boxes. After that, we are going to basically say, okay, let's do this one time by leaving this box 1 out and using all these 4 boxes to train our models. And once we train the models, we fit the models, so we have a model fit here. So let me just make this a little bit clearer here. Sorry about that. So once we have a model fit, I'm going to use this first box and put it into the model and trying to see how well it makes the predictions. But of course, we don't stop here. Well, since we already created these 5 boxes, of course, we do it one time. And then, obviously, we're going to repeat this process. So this is the first time we are going to leave out 1 box. And the second time we repeat the process, we are going to put box 1 back into the training group, but then we are going to take out the second box. So we are going to use the second box to test the predictions from the models that we trained with box 1, box 3, box 4, and box 5. That's the second predictions process. And of course, this process is going to repeat until when? Until we use up all these boxes to do our predictions. And what happened is once we get these 5 results, we are going to average it out, right? We are going to aggregate and average it out. So that's the whole idea about like the k-fold cross-validations approach. So here we're going to go back, right, to our examples in the out. So we come back here and let's try to do the 5-fold cross-validations. Again, for fit ones, we're going to use the cv.glm functions for cross-validations, and we define 5-fold. We extract the delta, which is the mean square error. So we got 24.33215. And here we're going to do the 5-fold cross-validation for fit 2, which is model 2. And we got 18.176. And we're going to do the same thing for fit 3, which is model 3. And we got 18.6122. And then we're going to basically say, hey, you know what? I don't trust this result. I want to actually do it one more time. I want to do a 10-fold cross-validations. So in this case, you can now actually do the 10-fold here by adjusting the argument here with 10. So we're going to put this into our 10-fold cross-validation. So again, we're using model 1, and we define using 10-fold, and we're extracting the mean square error. So we got 24.218. And the second ones, the second model, we got 18.13193. And the last model, model 3, from 10-fold, we got 18.297. All right, so again, you can actually store this result into an array or a vector, right? So I have the 5-fold MSE and the 10-fold MSE, and I'm going to put them into a data frame so I can actually see the result better. So we have the model fit 1, fit 2, fit 3, and also the 5-fold, 10-fold MSE reported in the data frame. Again, if you want to actually compare it to our previous results, you can definitely draw a purple lines in this case to represent the 5-fold MSE, and also the brown color lines to represent the 10-fold MSE. And again, if you want to update a legends here, right, to basically cover that up, right? So now here you go. Okay, so now we have all this MSE for model 1, model 3, and model 2 and model 3. You can now tell exactly which model it's most reliable when we are trying to use it for making a predictions for unknown data. And obviously, model 2 is the winner in this case. Model 2 is superior in every single test that we actually do here. So when you are doing your assignments or when you're running your projects, please make sure you at least use one or the two that we described here, either the validation set approach or using a leave one out, or maybe using a k-fold MSE. So to actually validate your result to see, well, how well your model it's used to make the predictions comparing to other specifications. In the previous class, we actually used different data sets, right, to do our predictions and trying to select models in different degree of polynomial. But you want to keep in mind that is not the limitations. We are using those examples for polynomials because it's convenience for us to do the for loops to create multiple models to compare. However, the reality is you can actually use this testing or validation approaches to validate the results from any models as a comparisons for the same purpose. So as long as you have different models, well, please try to consider using the validations approaches that we described here, and trying to make sure that you got the correct results or more trustable results, right? So from your buildings of the models. All right, so I'm going to stop the video here, and please review the problems, and also let me know if you have any questions about using the outs to run the cross-validations, or if you have any questions about applying it to your projects. So I will see you in the next video.